Is now this is an area of its own importance. This is a big area. Um, it's essentially an independent area which gets used a lot. So essentially what it does is that it tries to prove inequalities about probability measures or functions of probability measures. Now its intersection with optimal transport comes in its geometric interpretations of these inequalities. So let's try to do this. Let's try to do this slowly so that develop this. Much of the discussion will be formal because I'm going to just talk about Euclidean or Hilbert space ideas, how you should think of them in terms of optimal transport. The proofs are based on these ideas, but they are not directly transferable because Wasserstein space is not an Hilbert space. So you have to go back and actually see how the proofs are adapted. But the ideas are exactly this, the Euclidean ideas. So I start with my Wasserstein space. So fix RD, the Wasserstein space on RD. So I have P2 of RD as usual. This is all probabilities with finite second moments. And I equip this with the Wasserstein 2 metric. Right? So this is my Wasserstein space, the usual one. Now over this, I have a function. So let f from P2 of RD to R be some, so R union plus infinity, be some function that is lower semi-continuous and semi-convex. Semi-convex geodesically. Okay, so remember that semi-convex means that it doesn't have to be actually geodesically convex. It's just that its concavity has a lower bound. The Hessian, in some sense, has a lower bound there. So that's semi-convexity. Now, along with this, so once you're given such a function f, there are two things that you can associate with it. So associate with this, the gradient flow. Gradient flow rho t. So the rho t is the gradient flow of f, which means that rho t satisfies the following. So rho t dot divergence of Vt rho t is equal to 0, where Vt is a negative of the Wasserstein gradient of f at rho t. Vt is a negative of the Wasserstein gradient of f at rho t. Another alternative way of writing this is the following. Alternatively, you can write rho t dot is equal to divergence Wasserstein gradient f of rho t times rho t. Here, as usual, the Wasserstein gradient of f of rho t, f of rho, you should think of this as the gradient of the first variation of f at rho. Okay? So this rho t is a curve of probability measures. This is my Wasserstein gradient, my Wasserstein gradient flow of this function f. Everything depends on whether it exists, whether it's well-defined, those questions. We are just pushing this under the rug. Assume everything is well-defined and everything is nice. How do you actually prove that everything is well-defined and everything is nice? We write down this formal computation. It gives you a certain PDE, and then you use PDE theory to prove that this PDE has a weak solution. So this is one of the big benefits of the Wasserstein calculus. It always doesn't give you rigorous proofs, but it gives you a physics kind of proof. It gives you a proof which is formal, and then you can use your standard tools to prove that this, whatever formal idea you get from this, is actually true. All right, okay. Now, just like we did this calculation for the Hilbert space, one can write what is the dissipation rate. So what is the ddt of f of rho t? So rho t is my Wasserstein gradient flow of f. And now I'm asking, what is the time derivative of f along rho t? For a gradient flow of the Hilbert space, we did this calculation before. We know that ddt of f of rho t would be given by minus, this is going to be the Wasserstein norm square of this f of rho t. This is not very hard to prove in this case. As long as a Wasserstein gradient exists, you just apply autocalculus to it and you get this. But again, as I keep on saying, you can guess this from your Hilbert space calculation. But this is going to be this number. This quantity is what I'm going to call my d of rho. So this is what I'm going to call my d of rho. For example, when f is entropy, my d of rho is my Fisher information. When my f is relative entropy, my d of rho is relative Fisher information. So there are examples that we actually know. So I have these three quantities here. So three objects. One is f of rho, and associated with f of rho is rho infinity. This is the minimizer of f. Assume that this is unique. I have the quantity which is d of rho, which is the rate at which my f is decreasing along my gradient flow curve. And I have the quantity which is W2 square rho to rho infinity. So I have these three objects. So here you should think of rho as a rho zero. So you're basically starting a gradient flow curve starting from rho, and you're going to converge to rho infinity. And there are three objects of interest. One is f of rho, one is d of rho, and one is W2 square of rho and rho infinity. And the kind of inequalities that we are going to look at today are inequalities that involve these three objects. Okay, so we're going to bound one of them with respect to the other two. That's the kind of inequalities that we're looking for. So the basic idea should be, or a basic idea is, if f is semi-convex, one should expect three things to hold. What are these three things to hold? One, that D of rho dominates F of rho. This usually requires strict uniform convexity, but you expect, okay, some kind of semi-convexity condition should give this. D of rho should dominate F of rho. Two, F of rho.
What does that mean?
Oh, just means that F of rho will be less than or equal to some constant times D of rho. So this is something like saying F of rho would be less than or equal to some constant times D of rho. That's what it means by it.
Okay.
It's dominating by this.
Mm-hmm.
The second thing would be that F of rho minus F of rho infinity should dominate the W2 distance between rho and rho infinity. Same idea, that the right-hand side, the W2 distance should be less than or equal to some constant times F of rho minus F of rho infinity, where the constant will depend on the function and when rho infinity. And three is that D of rho and W2 rho to rho infinity should dominate. So together dominate F of rho minus F of rho infinity. Okay. So what I'm trying to say is that this is the kind of ideas that you should expect from the Hilbert space or Euclidean calculations. In fact, the first one, which is this, the number one that I've written down, this is what I called, by the way, this should also be F of rho minus F of rho infinity. The first one, in my last class, this is what I called my Polyak-Loasiewicz condition, PL condition, which says that the function is dominated by the norm square of the gradient. So that was a PL condition. So one should expect something similar to hold for the Wasserstein's case, at least when the function is uniformly geodesically convex. The second one, F of rho minus F of rho infinity, should dominate the W2 distance. This also happens if the function is lambda convex. In the Euclidean case, you can see this. It also happens, and this is what we'll call the Talleyrand inequality. The first one in the Wasserstein space goes by the name of log Sobolev inequality. The second one is the Talleyrand inequality. And the third one, which again is taken from the Euclidean or the Hessian case, this goes by the name of the HWI inequality. Okay. Let's see, for example, how the third one. I've done this calculation last time, but let's see what I mean by this number 3, that we should expect such an inequality from going back to my Hilbert space calculation.
For the how does the sign of F play in here? Because what if it's negative?
No, so that's why I'm always
Is the
subtracting
domination
F.
have a,
No, I'm always subtracting from F rho to F rho infinity, where rho infinity is the
okay,
minimizer
so that's
of
always
F.
going to
So
be
that is
positive.
always positive, always non-negative, right?
Okay,
Got it. That's why I made this change.
Yeah.
So let's say, for example, 3. So these are all inspired. So every one of these inequalities for the probability measures is a subject of its own. They're widely used in many, many fields, in physics, in PDEs, in probability. But they're all kind of inspired by this basic Euclidean calculations, at least the proofs that I'm going to, that are optimal transport based. There are other proofs which don't use optimal transport. So these are all inspired from Euclidean calculations or Hilbert space calculations. So let's check number 3. Let's check 3. So as an example, let's do 3. 1 I have already done. 2 I'll leave it for you to verify for Hilbert space valued functions, uniformly convex functions. So let's check 3. So let's again go back to our Hilbert space. So H is my Hilbert space. F is, let's say, lambda convex. for some lambda on the real line, and F admits a unique minimizer let's say x infinity. And so lambda convex means that if I take any lambda convexity means that if I take any z, then f of z is greater than or equal to f of x plus gradient of f of x, inner product with z minus x, plus lambda over 2 norm of z minus x norm square. If lambda is positive, then this gives me a bound on the gap between the curve and the tangential approximation. If lambda is negative, it does the same thing. It's just that the gap shrinks. Okay, now so this is true for all z. Take z to be x infinity, which is the minimizer of this function f. And then I get f of x infinity is greater than or equal to f of x plus gradient of f of x, x infinity minus x, inner product, plus lambda over 2, x infinity minus x, norm square. And so what I'm going to do is, again, rearrange terms. And I get f of x minus f of x infinity is less than or equal to gradient of f of x minus x infinity minus lambda over 2, x infinity minus x, norm square. And by Cauchy-Schwarz, I get this is less than or equal to gradient of f of x, norm of x minus x infinity, and then minus lambda over 2, x infinity minus x, norm square. So what am I doing here? I'm bounding the left-hand side, which is the difference of the function at x from x infinity. I'm bounding it by two quantities. One is the norm of the gradient of f at x times the distance from x to x infinity minus a constant times the distance square of x to x infinity. And so if I have to directly generalize to number 3, you can essentially guess what the theorem should be. If the function is C concave, if the function is lambda convex, I should be able to bound f of rho minus f of rho infinity by less than or equal to, this is my square root of d of rho, this is the norm. Then this is my w2 rho to rho infinity, and this would be minus lambda over 2 w2 square rho to rho infinity. Right? That would be my guess. So the fact that you can guess this is because of autocalculus. You can lift your Euclidean result and make a guess. How are you going to prove this? Well, to prove this, then you need regularity, you need smoothness, you need arguments. But based on how we derive this argument, this very simple argument, you can try to prove this. Okay, so let's go over some of these inequalities. So here is what Villani would call a meta theorem on the Wasserstein space. So I mean by meta theorem means this is the theorem that you'd expect for all these semi-convex functions in the Wasserstein 2 space. For some of these semi-convex functions, they have been rigorously proved. For others, if you want to prove them, you have to start from the basics and actually prove them. But this is a theorem that you should keep in mind that they should hold under ideal conditions. So your meta theorem is the following. So let f be a lower semi-continuous function on the Wasserstein space. So 1. Suppose F is lambda geodesically convex for some lambda positive then it admits a unique minimizer rho infinity, and for all rho in P2 of Rd, d of rho is greater than or equal to twice lambda f of rho minus f of rho infinity. Okay. On Hilbert space, this is what I called my PL condition. So this is my Polyak-Loasiewicz condition. This is my PL condition. A meta theorem would say that if I have my function f, which is lambda geodesically convex, then you should get this result. Is this theorem known for actual special cases? The answer is yes. And we'll come to this. So the example of this, where this has rigorously proved, is the case of the log-Sobolev inequality. Sobolev where my function f of rho is my relative entropy, or Kullback-Leibler, of rho with respect to rho infinity, which is e to the power minus v for some v which is uniformly convex. Okay. So for this quantity, the log-Sobolev inequality, so the function that I take is my Kullback-Leibler with respect to a uniformly log-convex probability measure. I know this Kullback-Leibler quantity is, this is lambda geodesically convex because I've assumed my potential V to be geodesically convex, is to be uniformly convex, lambda convex. For this case, my D function is my relative Fisher information, and f of rho infinity is 0. And this inequality then boils down to what is called logarithmic Sobolev inequality. And we'll write down a statement for this afterwards. So you can guess that this is what the logarithmic Sobolev inequality should hold, and you can prove it by either optimal transport way or other ways that is actually true. I hope I'm making this idea clear. Why I'm stressing on this meta theorems or formal theorems, I hope making this clear, that this gives you a good set of guesses of what should be true, and then you can rigorously prove them. So one is this. Two, so I'm continuing with my meta theorem. Two, same conditions as one, same assumption as in one. And then I get for all rho in P2 of Rd, I can control the W2 distance from rho to rho infinity by square root of 2 over lambda, the difference of the functions. F of rho minus f of rho infinity. Now, I'm going to leave it as an exercise for you to prove that this is actually going to be also true if I'm working on a Hilbert space and my function f is lambda uniformly convex over this Hilbert space. Replace the left-hand side by the norm of x to x infinity, where x infinity is the minimum, And the right-hand side, replace it by square root of 2 over lambda f of x minus f of x infinity, and verify from your Euclidean calculus that you should get this. Okay. So you get this idea that is true for Hilbert spaces. You make an assumption that this should be true in general. Now, for special cases, when things are nice and smooth, you can prove that this is indeed true. So example is this another famous inequality called the Talagram or T2 inequality. Again, same idea, where f of rho is a Kullback-Leibler of rho from rho infinity, which is e to the power minus v. So I can control, this is, look at what this inequality is saying. The W2 distance is usually very hard to compute, right? Because it involves an optimization. You don't actually have any bound on this. It's very hard to compute. But the right-hand side for Talagrand's inequality, when this is Kullback-Leibler, is something that might be reasonably easier to compute, especially if you know something about the density. And it is saying that if your base density is uniformly log concave, then you can bound the Wasserstein-2 distance by the square root of the relative entropy. Okay, that's this 2. And 3, so I'm basically following these 3 ideas here. So d of rho dominates this. That's my first meta theorem. The difference of the functions dominate the distance. That's my second meta theorem. And the third one is that the norm of the gradient and the distance will dominate the difference of the 2 functions. That's my third meta theorem. So this is my third meta theorem, is what I'm going to write down next. So 3. So if f is just displacement if f is lambda convex, geodesically convex, for some lambda in R, then one gets that f of rho minus f of rho infinity, this is less than or equal to W2 distance in rho to rho infinity, square root of d of rho plus, minus lambda over 2 W2 square between rho to rho infinity. Okay. This is, of course, the counterpart of the Hilbert space argument that I just showed before, where you're controlling the function difference from the minimum by 2 quantities. One is the square root of the norm of the gradient times the W2 distance minus lambda over 2 W2 square distance. Okay. And so an example of this is the so-called HWI inequality, where again, my function f of rho is Kullback-Leibler with respect to rho. Rho infinity is e to the power minus v. And now I don't actually assume that v has to be convex. V just has to be semi-convex. And so I just assume that the Hessian of v is greater than or equal to lambda times identity. Okay, so these are the 3 main inequalities that we're going to look into. Is this idea clear? Notice what's happening, the role of lambda here. If lambda is strictly positive, which means you have more
space
convexity.
should I think about? Should I
Sorry, go
think
ahead.
about the KL being in the space of whatever X is in? So X is in RD, so that's a...
Sorry, KL is a number, right? It's a positive number.
Yeah, but it's, what is this support?
Of the densities, they're all in RD.
They're in RD. Okay.
Yeah, everything is in RD. I mean, these all have generalizations to other manifolds, but I'm only going to consider RD. Everything is in RD. All my densities, they're all elements in the Wasserstein 2 space on RD.
Great.
Okay. Any other questions? Okay. All right, good. So that's a general principle. If these functions are not these functions that you're interested in, perhaps you're interested in a different function and you want to control these kind of inequalities, what would you do? Well, first you prove that such a function is lambda geodesically convex for some lambda in real line. If it is lambda is positive, then everything is good. The first two theorems would hold. If lambda is not positive, lambda is negative, then at least the third theorem will hold. So you have to prove, starting to prove from geodesic convexity, then you kind of know that these theorems should morally hold if there is enough smoothness, and then you try and prove them. Okay, so the role of lambda is very clear in 3. If lambda is negative, then you have to account for, so the important quantity is the square of the Wasserstein distance, which could be larger than the Wasserstein distance at all. Okay. All right, okay, so good. So let's look into the first one, the logarithmic Sobolev inequality. Again, you guys are okay? All right, okay, so let's look at logarithmic Sobolev inequality. Excuse me? This is a rather old and important inequality. It probably comes from something like 1960s. It's a very, very important inequality, which says the following. So we say that rho infinity, so this comes with a definition. Say that rho infinity satisfies logarithmic Sobolev inequality LSI with some constant lambda, where lambda is positive, if for all rho, which is any probability measure on RD, doesn't actually have to be in probably second, it doesn't have to have finite second moment. For any probability measure on RD, I get that the Kullback-Leibler of rho infinity is bounded above by 1 over 2 lambda, sorry, 1 over 2 lambda relative Fisher information from rho to rho infinity. So this is my relative Fisher information. Which is the norm square, the L2 norm square of the gradient of Kullback-Leibler in L2 of rho. But you can also write it more explicitly as the integral of the norm square of the gradient of the log over rho infinity norm square du. So log Sobolev inequality is a property of rho infinity. Some probability measure rho infinity satisfies a logarithmic Sobolev inequality with a constant lambda. If for any other probability measure, I can bound this relative entropy of rho from rho infinity by a constant 1 over 2 lambda times the relative Fisher information. So relative Fisher information dominates the relative entropy. Okay, now when I first had started seeing this inequality, I was like, okay, why is this important? It seems like I don't understand relative entropy. I don't understand relative Fisher information. I have no clue how to think about these two things. And this is, you don't quite understand the importance of this inequality until you see these things in actual practice, like in applications. Optimal transport gives you a geometric way to understand this. I understand PL inequality. It says something about the growth of convex functions. The PL inequality, the Polyak-Lower-Seritz inequality says that the function growth can be bounded by the norm of the gradient. And to me, at least, the most intuitive way of thinking about log-Sobolev inequality is the same geometric idea, that if I'm looking into Kullback-Leibler as a function in Wasserstein space, then the growth of the function is dominated by some kind of norm, some norm of its gradient. So what is actually optimal transport saying here? So one can furnish a proof. So one can furnish an OT proof of the following theorem. So let V be a C2 function, so twice continuously differentiable function, on RD with integral of e to the power minus v is equal to 1, and Hessian of v is greater than or equal to lambda times identity, or some lambda positive. Then the measure e to the power minus v, rho infinity, satisfies log-Sobolev inequality with constant lambda. This is, of course, exactly what I anticipated from my meta theorem, but I'm now saying that this theorem is actually true, and you can prove this. The only extra assumption that I'm using here, that this is a C2 function. Good. And so you can prove this thing is true. Actually, other theorems are actually known for logarithmic Sobolev inequalities. So let's go over one of the other very widely used theorems for Sobolev inequality, which is called the Hawley-Stroke perturbation theorem. So here are some related theorems.
Did we state the HWI inequality? Because I
Not
thought
yet.
we didn't, and then, oh, we're still building up to it?
Yeah, so I'm kind of going in like 1, 2, 3. So 1 is my log-Sobolev inequality, which is where I am now. 2 is my Talleyrand inequality. I will go there next and talk about its relationship with concentration of measure. And 3 is the HWI inequality. I'll come to that at the end.
Okay.
Okay. So related theorems about logarithmic Sobolev inequality. So this theorem is sometimes called the Hawley-Stroke perturbation theorem. So the theorem says the following. Suppose rho infinity satisfies logarithmic Sobolev inequality with some constant lambda. Now define rho infinity tilde to be e to the power minus small v times rho infinity, where v is bounded. Then rho tilde infinity also satisfies LSI. Also satisfies logarithmic Sobolev inequality, not LSD, but LSI, with some constant lambda tilde, where lambda tilde is equal to exponential -2 supremum of v minus infimum of v this exponential is now closed times lambda. Okay. So what this is saying is that the logarithmic slope of inequalities are stable under bounded perturbation. You take one probability measure that satisfies logarithmic slope of inequality, and you add something which is, or you multiply it by some other function that is bounded. Then the probability measure that you get from it also satisfies logarithmic Sobolev inequality, and the constant now changes, and the constant is affected by this bounded function in the way that you take the original constant lambda and then you multiply this by exponential of -2 supremum of v minus infimum of v. So of course, this is the oscillation, the range of the function, supremum minus infimum. If the function is a constant, this is 0, so you get back lambda. Otherwise, it has a negative effect on lambda. Okay. By the way, I say the word negative effect on lambda. It should be quite clear that the bigger the lambda is, at least for an application point of view, that's better. Because if lambda is bigger, then you're getting more uniformly convex, so your gradient flows will converge faster. Okay, so this is the Holly-Stroke thing. The other question that you must ask is that what kind of densities are actually satisfying my logarithmic Sobolev inequality? So my theorem here says that if I take a C2 function such that which is lambda uniformly convex, then e to the power minus v satisfies logarithmic Sobolev inequality. Is the converse true? Can I say that anything that satisfies logarithmic Sobolev inequality must be of this type? Well, Holly-Stroke says no, not quite. First of all, you can perturb it by some bounded functions, and that still satisfies logarithmic Sobolev inequality. But the next theorem says that, well, it should at least have Gaussian tails. It must be sub-Gaussian to satisfy logarithmic Sobolev inequality. So that's my next theorem. So this is thing, and there is a theorem here, which is a necessary condition. Condition for LSI. And the theorem says the following, that if rho infinity satisfies logarithmic Sobolev inequality, then for some alpha positive, we must have that integral of e to the power alpha mod norm x square d of rho infinity must be finite. Okay. So rho infinity satisfies logarithmic Sobolev inequality if that it must have at least sub-Gaussian tail. Which, by the way, brings us to the question: are all normals, so are all multidimensional normal random variables, do they satisfy logarithmic Sobolev inequalities? What do you think? If you take standard normal, take a multidimensional standard normal, this would satisfy logarithmic Sobolev inequality. And this again follows from our first result that it is going to give you a C2 function whose Hessian is this. Okay. So in particular, if you have a lower bound, so if you take a multidimensional normal random variable with sigma as its covariance matrix, and that sigma has all eigenvalues positive, so it's strictly positive definite, then that multivariate normal distribution is going to satisfy logarithmic Sobolev inequality. Right? That follows from the first theorem. Is this clear? One of the consequences of logarithmic Sobolev inequality is that the gradient flow of Kullback-Leibler converges exponentially fast with this rate lambda. which means that the corresponding diffusion that you get from it, the Langevin diffusion, converges exponentially fast, and you measure it in Kullback-Leibler. Good. So a consequence of LSI is that the gradient flow converges at an exponential rate. Lambda, this means the Langevin diffusion for rho infinity converges exponentially fast. In the sense that the Kullback-Leibler the oh god, in the sense that Kullback-Leibler of rho t to rho infinity, this is e to the power minus lambda times t, constant c0. Good. So that gives me rate of convergence when measured in Kullback-Leibler. Good. The second question that you can ask is that, okay, I can measure the distance between rho t and rho infinity in Kullback-Leibler, but I can also measure the distance in W2. So the question is W2 distance between rho t to rho infinity converging exponentially fast? Well, in this, it would be nice if I could bound my W2 distance by the Kullback-Leibler and say Kullback-Leibler is converging exponentially fast. Therefore, W2 distance is also converging exponentially fast. When can I do that? Can I always do that? The answer is you cannot always do that, but you can do that when you satisfy Talleyrand inequality, which is the second theorem here. Right? The W2 distance is bounded by some square root of the function that over which you're taking this gradient flow. Are you following still so far, following what I'm saying? Okay. All right, I don't hear anything, anybody saying no. So let's write down what is the Talleyrand inequality. Okay, so definition. So let's we say that rho infinity satisfies the Talleyrand inequality, which is named after Michel Talleyrand. T or T2 or T2 with a constant lambda if for all of the probability measures, right, I can bound my W2 distance from rho to rho infinity by square root of 2 over lambda, the relative entropy of rho to rho infinity. So say that rho infinity satisfies Talleyrand inequality with constant lambda if this happens. Now the theorem that again you prove by using optimal transport is that if your rho infinity again is of the type e to the power minus v, where v is uniformly convex, then it does satisfy Talleyrand inequality. Okay. So theorem. So if your rho infinity satisfies logarithmic Sobolev inequality with constant lambda, then it satisfies Talleyrand inequality with the same constant lambda. In particular, if rho infinity is of the form e to the power minus v, where the Hessian of v is greater than or equal to lambda times identity, then rho infinity satisfies Talleyrand inequality T2 of lambda. So in particular, all of these multidimensional normal random variables, multidimensional Gaussian random variables, as long as you have a strictly positive definite covariance matrix, they will satisfy Talleyrand inequality. So if you are trying to compute a W2 distance of some probability measure with respect to some multidimensional Gaussian, what you really have to compute is the square root of the Kullback-Leibler distance, or relative entropy with respect to this Gaussian. And then with this constant, this eigenvalue constant, that will always give you an upper bound. Good.
Is there any theory for how tight that bound is?
So it is known that Talleyrand inequality does not imply logarithmic Sobolev inequality, so the other way does not go. And so Talleyrand inequality is strictly weaker, if that answers your question. Okay. One of the reasons why Talleyrand's inequality is popular is because it implies a phenomenon. Okay, I'm still hearing echo from somebody's mic. Thank you, Jeffrey. Is because of its relationship with a phenomenon which is called concentration of measure. So let me write down what is now called this beautiful argument by Martin, so Martin's argument, and see why this inequality is so particularly important. Talleyrand's inequality is important. So here's an aside. Talleyrand's inequality is important because it implies concentration of measure phenomenon. Okay, you may have heard this word concentration of measure. This is by now very, very widely used in every single area of applications of probability, or even in pure mathematics. What it says is the following phenomenon, which is true for many, many probability measures in high dimensions. So this is a phenomenon of probability measures in high dimensions, property of probability measures in high dimensions. Which says the following, that if you take a set B, so say rho infinity is some probability measure, rho infinity is some probability measure in RD, and take a set B such that the rho infinity puts a mass on B, which is, let's say, a half. So like a median kind of set. So you have taken a set such that half the mass is in B. Then the concentration of measure phenomenon would say that if you increase this set B, but even a tiny amount, then you have almost mass 1 inside that tiny amount. Okay, that's the idea of concentration of measure. So a tiny extension, a tiny expansion of a median set B basically contains the entire mass of the probability measure. So how do I make such a statement? How do I make such a statement precise? Okay, so for T positive, define BT to be the T expansion of X. So this is all Y in RD, such that the distance of Y from B is less than or equal to T. Okay. And the concentration of measure phenomenon says, so rho infinity satisfies concentration of measure if the rho infinity of BT, this is almost 1. So this is written equal to 1 minus some little o of 1, where this quantity depends on T and the dimension D. Yeah, I'll give an example. I'll show exactly an example. So if you fix your T and you take this dimension to be very large, then even a tiny amount of T expansion around this median set B will basically contain your entire mass of this probability measure. Okay. So that's basically the idea of concentration of measure. You see this in many common examples. So for example, if you take uniform distribution on a very high dimensional cube, if you take uniform distribution on a very high dimensional cube, the measure is very tightly concentrated around a sphere. You extend it a little bit, it contains almost the end mass. The same is true for the multivariate, let's say, standard normal distribution. Okay, these are based on independent coordinates, but there are also dependent measures which satisfy this. Of course, not all measures satisfies this property, but many measures that appear in computations or applications do satisfy this property. So a theorem that we will do now is that
it seems like
B
is really important, because you could it refers specifically to the set B, and if you pick for the multidimensional Gaussian, if you pick the origin, well, it's not tightly around the origin, it's tightly around the shell.
Of course.
But for any distribution, couldn't you just find a B where you could take B to be almost the whole thing? Or isn't the important thing that there's a unintuitive set B that has its concentration?
No. This is for any set B which has half the mass. You take a probability distribution. Any B which has half the mass is going to satisfy this.
Okay, that's the important thing here. Yeah.
So you can take a one-dimensional statistic and consider its median, and take the set B to be anything that is contained inside this median, inside this median ball, and that would also satisfy this. All right. Okay. So the theorem is that if rho infinity satisfies T2 inequality with lambda, then it satisfies it satisfies concentration of measure. So the theorem is, if rho infinity satisfies T2 of lambda, then it satisfies concentration of measure. And I'll write down a precise statement of what do I mean by concentration of measure. Give me a moment. But let me write down this argument. This argument, which is due to Martin, is based on optimal transport. This is actually now called Martin's argument. It's a beautiful argument, makes use of optimal transport, so it's a good exercise to see how you can use optimal transport. All right, okay. So I'm going to use Martin's argument. So take some B such that rho infinity of this set B is 1/2. So some median set. Okay, now consider BT as above. So for some T positive. So what was BT again? The thickening. BT is I'm looking into the T neighborhood of B. So I just thicken it by putting everything that of distance T from B. Now I'm going to consider two different probability distributions. So consider two probability distributions. One is mu, which is rho infinity restricted, so conditioned on B. So what does this mean? It means that mu of A, this is rho infinity of B intersection A divided by rho infinity of B. Could make sense. And nu, which is rho infinity conditioned on BT, the BT complement. So again, what is nu of any set A? This is rho infinity BT complement intersection A divided by rho infinity of BT complement. Because so I'm looking at two conditional distributions, two conditional measures. One is rho infinity conditioned to lie inside B. The other is rho infinity conditioned to lie in the complement of BT. Make sense? It is obvious that if I look into W2 distance between mu and nu, it must be at least T. Why is that? The question to the audience, why is the W2 distance between mu and nu, these two probability measures, must be at least T? No? The distance between B and BT complement is at least T. So if I have a probability measure that is supported on B and another probability measure that is supported on BT complement, the distance I'm transporting it must be at least T. And so W2 distance must be at least T. Are you following what I'm saying?
Yeah, that makes sense.
Okay, good. So then W2 distance between mu and nu must be at least T. But by triangle inequality, I get that this must be less than or equal to W2 distance between mu and rho infinity plus the W2 distance from mu and rho infinity, right? Because W2 is a metric and it satisfies triangle inequality. And therefore, now by the fact that rho infinity satisfies T2 inequality, I get that this is less than or equal to square root of 2 over lambda, Kullback-Leibler of mu from rho infinity, plus square root of 2 over lambda, Kullback-Leibler of nu from rho infinity. This is where, because of rho is in, rho infinity satisfies T2 lambda. This is where I'm using this. Now, what is a Kullback-Leibler or relative entropy of mu with rho infinity? So mu is just rho infinity conditioned to be in B. Okay. If you quickly compute this thing, I'll leave for you to check this, verify this, that if you compute this, you'll get that this is exactly equal to square root of 2 over lambda log of 1 over rho infinity of B. Right? Mu is exactly rho infinity, well, divided by rho infinity of B. The density is divided by rho infinity of B inside B and 0 otherwise. So when you take the likelihood ratio of mu with respect to rho infinity, you get 1 over rho infinity of B inside B and 0 otherwise. And so you get exactly this quantity. Okay. And then I get the other one, which is square root of 2 over lambda log of 1 over rho infinity of BT complement. Now this I have already taken this to be 1/2. So this quantity is square root of 2 over lambda log 2. And so therefore, from the fact that T is bounded by this and that, I can now rearrange terms and get a bound on rho infinity of BT. So rearrange your terms. So from the fact that this sum of these two is greater than or equal to T, so by rearranging, the terms, I would get that rho infinity of BT is greater than or equal to 1 minus e to the power minus lambda over 2 and T minus square root of 2 log 2 square. And so what you see from here is that this is a Gaussian tail. Right, so this is a Gaussian tail with this constant lambda determining how fast it is dropping. But that basically gives me my concentration of measure phenomenon, which is that I take any set B, which is a median set, and then if I look at the mass from a T neighborhood of B, then it's dropping fast. How fast? Like a Gaussian, which is roughly e to the power minus lambda over 2T squared. Okay, and so the measure is basically getting concentrated around this median set B. Do you understand what I'm saying here?
Yeah,
So
there's no dimension in that.
There is no
Gaussian
dimension
tail.
in it. Exactly, there is no dimension in it. This is completely dimension free. There's no dimension in it. As long as you, of course, know what lambda is. Okay. So this is the
Think about the
concentration.
right way for lambda. If lambda's big or
Well,
small.
you should. Well, so yeah. Okay, I'll say a little bit about it. W2 squared, for example, is additive in dimension. If you take independent coordinates, it adds the things up. You can actually show that the relative entropy is also actually additive. Relative entropy of it has a factorization property if you take independent coordinates and the Kullback-Leibler adds up. And so really the way that this is growing is both of these are actually growing of the constant of square root of D on both sides. And so you can actually take lambda to be dimension free, which is also what you get from the LSI. You get dimension free constants. Okay, if you properly scale it. So anyway, so this is what I mean by my Gaussian tail, and this is what is the conservation of measure phenomenon. So rho infinity exhibits concentration of measure. Isn't this such a cool argument? It's like just half a page argument using optimal transport. It gives you this deep theorem of concentration of measure of any probability measure that satisfies T2 inequality, Thaler-Bunsen inequality. I love this argument. Just like a single page argument. Anyway, that's what makes this argument so famous. All right, I should also mention one more related theorem, which is, you may already know this, the Zeiser-Kullback-Pinsker theorem. So this is a related theorem. So Zeiser-Kullback-Pinsker inequality. Sometimes it's just called Pinsker inequality, depending on which community you're talking to. Pinsker inequality, which says that the following is true. That no matter what rho infinity you look at, for any rho infinity, I get that the total variation distance, so rho minus rho infinity, total variation distance, is bounded by twice the Kullback-Leibler of rho to rho infinity. So your total variation distance is actually easier to bound, but then that doesn't actually help you in W2 squared distance or Wasserstein 2 distance, because that one requires some property of rho infinity. But we know that if rho infinity is uniformly log concave, then it does satisfy Talleyrand inequality, and you can bound W2 by Kullback-Leibler. Okay. All right, good. So finally, we get to the HWI inequality. This is the last bit of it. So HWI inequalities. This is originally discovered by Otto, and there's a work of Otto and Villani. HWI inequality. So H stands for Kullback-Leibler because in physics you often write H for relative entropy. W is, of course, Wasserstein 2 distance, and I is information for Fisher information. So HWI inequality. So let rho, so this is Otto and Villani. So let rho infinity be e to the power minus v, such that the Hessian of v is bounded below by k times identity for some k on the real line. For some k in the real line. Assume that it's finite v e to the power minus v. This is actually finite. Then for all rho which are in P2 absolutely continuous in RD, we get that the Kullback-Leibler of rho to rho infinity, this can be bounded above by W2 distance of rho to rho infinity, square root of the relative Fisher information of rho to rho infinity, minus k over 2 W2 square distance between rho to rho infinity. So this is like a converse. If you know W2 distance, in general, you cannot bound relative entropy. And there is a geometric reason for this. If you think about how W2 distance is doing, you're moving mass. You're making horizontal movements. You're making moving mass horizontally. On the other hand, if you look at how Kullback-Leibler is behaving, it's comparing the densities at the same point. So it's like vertical comparison. And in general, you cannot compare horizontal movements with vertical movements. It's just not simply possible. So there is no hope of controlling relative entropy by Wasserstein 2 distance. What this is saying is that if you have some bound on the Fisher information, then you can control Kullback-Leibler given the Fisher information and the Wasserstein 2 distance. As long as the measure rho infinity is log semi-convex. So log semi-convex, you can do this. And the theorem is exactly what we anticipated. The Kullback-Leibler rho to rho infinity is bounded above by the W2 distance from rho to infinity, square root of the Fisher information, minus k over 2 W2 square. Okay, so if you're looking at a row which is very close to rho infinity in a small neighborhood, that's when the Fisher information comes into play, because W2 square becomes negligible. This is very close to zero. That's not the leading part. That's where this term becomes independent. If you have control over Fisher information, you have control over relative entropy. On the other hand, if you're looking at a row which is very far away from rho infinity, then the second term actually dominates. Actually, the first term can also dominate. They both can dominate. And so you're getting some bound involving both of these terms there.
This is exactly the upper bound.
This is the exact
For
upper
the
bound.
other,
Yes.
for the, we have, yeah, it's the Fisher information is this extra piece and whatever this constant K is. So it sort of squeezes we have the KL in between the W2 on the left-hand side with the square root that we
Correct.
did earlier, and then
Correct.
now here.
Correct. This is again, I will go back to this goal that I said at the beginning of this class, that 1, 2, 3, we want to basically say how to control each of these terms with respect to the other two. And that's basically what we are showing. So D is my Fisher information, F is my Kullback-Leibler, W2 is my function, and I want to say that one of the, given the other two, I can control the third one. This meta theorem should be true under enough smoothness for all geodesically convex functions F, but specifically the things that we have written down are the most important cases, which is the case of Kullback-Leibler with respect to a uniformly log concave function. All right. Okay, good. So I'll stop here. The proofs of these inequalities, you can find in this many textbook. For example, Villani gives a very good treatment of it. Many of these actually HWIs, this is due to work of Villani. So there's optimal transport based proof is actually given there. But each of these inequalities have many more extensions, many more generalizations, and some of them don't use optimal transport. So it's this optimal transport gives a very beautiful geometric intuition of why these inequalities should be true and what you should anticipate if you want to come up with other inequalities. If you want to come up with other inequalities involving these three objects, your first line of thinking should be, is this even true for the geometric setting of a Hilbert space? If it is true, then you should try to generalize it to optimal transport. All right, okay. So I'll stop here. If you have any questions, ask me now.
I have a bit of a researchy question about.
Yeah.
So at the Fields meeting, there was this talk on distributionally robust optimization by Jose Blanchett. And he talked about these connections between KL and Wasserstein distance. Now, in the context of trying to solve an inverse problem, but then learn solving a fittable prior, like empirical Bayes, learn the prior, learn, rho infinity when we're actually sampling from rho, an estimate of rho, how we have a fixed forward model. Is this theory the sort of connection where we can, because there's results that show like peakiness for KL type empirical Bayes objectives, where it collapses to specific measurements you have, the prior ends up peaking around those, and it's not distributionally robust, it doesn't generalize, it's not smooth. But I've been trying out some simple problems of like having sets of shapes that have distances with each other, and these Wasserstein distribution to distribution objectives are very they're very smooth, they're very robust, and there's a little bit of a bias to them, but it doesn't seem like that big of a deal compared with like kernel density estimators and empirical Bayes methods. So I'm just wondering if all this stuff is worked out and known, because it's really not used in my field at all. And it's you can quickly compute, you can have a likelihood matrix, have uniform marginals on like your measurements and your samples, and then compute a gradient based signal through like gradient based OT all the way through to your latent variables. And it's if you have like 100 by 100 standard OT problem to solve. It's quick. You get a gradient signal, you take a step, and then you just kind of iterate this. So I haven't seen that in my area, but it seems to be working, and I don't know if there's like a lot of theory about it.
Okay, so first of all, okay, I'm not the right person. I'm not an expert here who is, but I would say that much of what I've learned from listening to talks on these things is that no, it's completely unknown. So these kind of problems. So well, one of the reasons of this workshop is that you're really learning about these problems with the very forefront of things. So DRO, for example, widely used in practice. We still don't have a much good of a theoretical understanding of this. So if you have come up with something new that works, your first guess is that maybe it's not known, and you should probably check with an actual expert, like write to Jose and actually check that this is actually known or not. The other thing is that exactly, so what I'm trying to say here is that it has been observed over and over again that Wasserstein-based methods are very robust. That's exactly why people like about it. And Kullback-Leibler is very fragile, so people don't like about it. On the other hand, Kullback-Leibler has many other interesting theoretical properties. And so what these kind of theorems are basically telling you is that under what conditions you can go from one to the other. So if you know something about Wasserstein, maybe you can control Kullback-Leibler. If you know something about Kullback-Leibler, you can control Wasserstein. But these are, of course, very theoretical results. If you don't know what rho infinity is, none of these theorems will actually apply. So,
Okay, thank you.
Any other questions? All right, okay. If not, thank you all for coming, and let's see you guys on Friday.